I will talk about resampling methods. This subject is the carrier of statistical and machine learning methods. And so they involve repeatedly drawing samples from a training data set, and refitting a model of interest on each sample in order to get that additional information about your fitted model in here. And please keep in mind that these methods or resampling approaches can be computationally expensive because they are just fitting the same statistical method multiple times using different subsets of your training data sets. So I want you to just think deeply about the following questions. How would we select a good model? Okay, and the other one is, do you remember any statistical method? In here, maybe you should go into deeply your previous information in here, then just check out which statistical methods do you know. Let's say you want to compare the regression models with linear, ridge, and lasso. For example, you are trying different lambdas, so now you do not only choose the model, you also choose your hyperparameter in here, okay? And so we have another questions in here. How would you compare different models and methods? Okay, so you find your lambda, you find your betas. So we will also choose lambda and we will get a model in here, okay? And I have my data set and I compare different methods in here. And then I can say that I'm going to use that model in here. So in this video, we will see how to choose a parameter, how to find the performance, and how to choose one of the algorithms in here. And of course, there are several ways, and we will see some of them. And the other one can be that you fit your model to the training data. And is it possible that you can generalize it to an unseen data in here? And here is the assumption. We assume that the training examples are IID, which means independent and identically distributed. And if you're familiar with the statistical concept, this is one of the main assumptions we have in there. And this means that all your examples have been drawn from the same probability distribution, and they are statistically independent from each other. This is a very important assumptions, the methods we will use. And so use test data only once to reduce bias. Okay, this is another important point I want you to remind. And also, throughout this video, we will try to find, or we will look for a systematic methodology in here, okay? Of course, you can try different model, different hyperparameters or different inner parameters in your model. But it is important to find a way to get a systematic methodology in here to make sure that you make a scientific way of choose your methods in this concept. So let me give you some terminology in here. The first one is the prediction accuracy, which is defined as the number of all correct predictions and divided by the number of examples in the data sets in here. And we generally show that as ACC. And so ACC is 1 minus ERR. And ERR is the prediction error in here, which is computed as the expected value of 1-0 loss over n examples in a data set as in here, okay? And maybe you can see ERR for S data sets as following in here. And when we just look at for this loss function, you see that this loss is defined like this one. It's going to be 0 when your prediction is equal to real value and 1 if it is not, okay? So since we are talking about the loss, and you see that we are giving 1 if they are not equal to each other. And you will see that the yi is the I true class label and yi hat is the I predicted class label respectively in here, okay? And when we continue with this terminology in here, you will see that we will give just the bias and variance. And so bias is statistical bias in this concept. And here is the explanation of the bias. You have the expected value of your beta hat minus your beta. And also we can find the variance in this concept, and it is the measure of the variability of a model's prediction if we repeat the learning process multiple times with small fluctuations in the training data sets in here. Okay, and we will be talking about this terminology or using this terminology throughout this topic for this video. And so, what will happen in general in resampling method is that we will have three concepts mainly. Okay, first one, we have the algorithm and we have model parameters on hand. Okay, we know them. But we may be trying to find a way to generalize our performance. Okay, this can be one of the cases you are looking for, or your algorithm is known and you want to do model selection. Okay, and please keep in mind that the process of evaluating a model's performance is known as model assessment. But the process of selecting the proper level of flexibility for a model is known as model selection in here. Okay, so if you want to do that model selection in here, that means you look for hyperparameters. Okay, different models in this concept mean different hyperparameters, such as K in KNN. Maybe you are familiar with that concept. Okay, this is the second case we may be looking for. And another thing for us is to do algorithm selection. Okay, so which one you want to use? Lasso, KNN, Reach. It is up to your data and it is up to your aim in here, and you may also want to choose one of the algorithms in here. So for these three main aims, we will be looking for a systematic way to just check for these guys in this concept in here. Okay. And resampling methods involve repeatedly drawing samples from a training set and refitting a model of interest on each sample in order to obtain additional information about the fitted model. Okay, and please keep in mind that they are computationally expensive because they involve that fitting the same statistical method multiple times using that different subsets of your training data sets. And yes, is resampling computationally expensive? I think I already gave the answer in here, and we will see that if they are really feasible in there or not. So let me continue with this resubstitution method. And this is one of the basic one, but not commonly used. Let's see what is happening in here. So you know the model in here, and that means you choose your hyperparameters. So here is my data. I have my whole data, and I'm just training my algorithm in here by using these data sets. Okay, and then I just run the model again with my data sets. Please keep in mind that the training data and also the test data is the same in resubstitution. Okay, so for example, we use the lasso with lambda equals to 20. Okay, and then let me run data with this algorithm. Then let me apply and compare the model in the same data sets in here. Okay, and after that we can just check for the performance in this method. And here is the big difference of this method, that it used the data, the same data set for training and test. Okay, but at the end of this method you will see that you may have some optimistic bias due to the overfitting, since the training and test data are the same in here. And in other words, we may say that we cannot tell whether the model simply memorize the training data or whether it generalizes well to new and unseen data in these methods. Okay. So another alternative is the holdout method. So let's see how it is working, and please keep in mind that it's a very general name for this kind of methods in here. In holdout, you have your data and you just split your data into two with training and test, okay? And after that, you just train your algorithm by using these trained data sets. And then you just run your model with your test data sets in here. And you just repeat that one with another training data. And also just run your model one more time to your test data sets. And again, you just train your model or your algorithm with training data. And also you just test your data set with the model in here. So at the end, you have several performance. One's performance from this blue data and the other one, like this blue data, and the other one is coming one from this one, and also the other one is coming from the green test set in here. And if I split the data in another way, I would have another training and test set corresponding to the blue one in here, or the green one in another distinction, okay? And here is the question in this method. I have several performance right now. Please remember that we have several performance from several types of splitting in here. What would I do now? Okay, please stop the video and think about it. And the answer can be that I can even get the average of my performance from each training and test data in here, okay? So when using that holdout methods, and there is one problem arising, which is stratification. And please remember that a data set represents a random sample drawn from a probability distribution. And we typically assume that this sample is representative of your true population, more or less in here, okay? Further, resampling without replacements alter the statistics such as mean, proportion, and variance of the sample. When we randomly divide a labeled data set into training and test sets, we violate the assumption of statistical independence in here. Let's remember the iris data set. We have the species in there, Setosa, versicolor, and Virginia. Please assume that the iris data set is representative of the true population. For instance, assuming that iris flower species are distributed uniformly in nature. You will see that they are uniformly distributed for each species in here. And we just created, this is your true population, and we just created two imbalanced data sets with non-uniform class distribution. So the class ratio that the learning algorithm used to learn the model is, which is training set, 38%, 28%, 34%. It's slightly different than the previous one. The test data also is used for evaluating the model, is imbalanced as well, and even worse in here. It is balanced in the opposite direction actually. You have 24%, 44%, and 32%. Okay, let's try to get the idea by a graphic in here. The first one just showed the frequencies of the variable sample width, and you will see that it is for all samples, and the sample size is 150. And you see that the Setosa in blue, Virginia in orange, and versicolor, the versicolor in yellow, I guess, in here. Okay, we have our true population like that. When we check out for our training samples with 100 sample of size in here, you will say that it is okay, it's kind of a representative of this population, but not that much. And the test data is even worse. And you see that we have some doubt that our test sample may not be representative of the true population. And this can cause some problems in this method. And we may see some solutions in here. So here is the first one. You can divide the data set in a stratified fashion in here. So stratification simply means that we randomly split a data such that each class is correctly represented in the resulting subset, okay, which are training and test data sets. But please keep in mind that the random subsampling in non-stratified fashion is usually not a big concern when working with relatively large and balanced data sets. So if you have a really large data set, you can be more relaxed. Because it's kind of not that problem when you have big data sets in here. But please keep in mind that there are several studies that shows that stratification has a positive effect on the variance and the bias of the estimations. For example, in k-fold cross-validation, you can just check out this paper to get the idea in there. All in all, here are the three main aims of today: model selection, algorithm selection, and performance generalization. And here is the model selection. So we have our algorithm and we have set of hyperparameters in here. For the first set, let's run the model. And for the second set, we run the model again, the same model. And for the M set, we run the model again. For each model, we are just looking the performance. And at the end, we are just choosing one of them by looking at this performance in here. Okay, let's say we are using elastic net and we use two different hyperparameters, lambda 1 and lambda 2. And we want to choose, maybe you remember that the elastic net has two parameters in that model. And so for each of these lambda, we want to choose some grids for both, and each combination of the elements in this grid will be one set of hyperparameters in here. So we will run the model for each set, okay? For each set in here. Here are set 1, set 2, and set M. For example, I divide the data 20 different ways for each model. In the principal model, I get 20 performance and average it. Then I get 20 performance in the same way with other models. I can get the average at the end of the day. Okay. And how algorithm selection is working is that we have our first algorithm and we try several models for this algorithm. That means several hyperparameters. And we have the kth algorithm and we are just using different models for that algorithm too. And why do we have different model for the same algorithm? When you just check out, for example, this is the same algorithm, but we have different models in here. And this guy is another algorithm, but it is same for each model in here. Why do we do that? So please keep in mind that they all have different hyperparameters. That is why we are doing them with same hyperparameters in here. Let's say in this model is the same with this one. But at the end of the day, we will choose one of the algorithms in here by looking at this performance in here, okay? And the last one is the performance generalization. We know the algorithm and the parameters. That means we have the model. So now they know both of them, and they do not want you to change the algorithm or the parameters in here. So you can only play with the data and find a way to say something about the performance of these models. They say that please use this model like lasso with this parameter, okay? But say us something about the performance of this model. What can you do that? You have your algorithm, you have your model, you know them, and you can just try different set of training and test data, and again training and test data, and again training and test data. By looking at these data sets and by playing with them, you can just say something about the performance of this model in here. So let's talk about that holdout validation. First, we randomly divide our available data into two subsets, which are training and test data. And so far, you are kind of familiar with this concept now. So here, the test set shall represent new unseen data to the model. And it's important for that model, the test set is only used once to avoid introducing the bias when we estimating the generalization performance in here. Okay, so after setting test example aside, we are just picking a learning algorithm that we think could be appropriate for the given problem, and by specifying hyperparameters manually in here. Okay, so please keep in mind that the learning algorithm does not learn the hyperparameters from the training data, but it learns the actual model parameters. Okay, and so for now we have to go with some fixed hyperparameter values in here. After the learning algorithm fits a model in the previous step, the next question is how good is our performance of the resulting model here. Okay, this is where your test data came to the play. Okay, since the learning algorithm has not seen this test set before, it kind of provides a relatively unbiased estimate of its performance on new, unseen test data in here. Now we can just use this test set and just use our model to predict the class labels. Then we can just take the predicted class labels and compare them to the correct class labels and estimate the model's generalization accuracy of error, which is delta in here. Okay, and red delta is your performance, and it can be, for example, MSE in the case of a quantitative response, which provides an estimate of the test error rate in there. Okay, this is an example in here. And after all this procedure, as a rule of thumb, you have one last training in here. The model will have a better generalization performance if the algorithm uses more informative data. Assume that it has not reached its capacity yet. Okay, you have used some part of training data sets, but also you had to just split the data and use that test data sets to get some accuracy measurements in here. But in the end of the day, we run the model one last time with all data sets and get the final product. Okay? Let me give you a brief example in here. Let's say I use Lasso as an algorithm and train my data set with this algorithm. This is Lasso in here. What is training in Lasso is that just finding the betas in the model. Okay? You are just finding betas in this step. And for a specific hyperparameter, you have a specific model and you can use that model with your test data and find your performance in here. That's, I think, kind of simple. You use training data set to train your model, and to train your data in here and find the model, and then you use the test data to see the performance of your model in here. So when we run the holdout method just once, the performance may be affected by this training and test data sets. So one way to obtain a more robust performance estimate that may be less variant to how we split the data into training and test sets is that repeating the holdout method k times with different random seeds and compute the average performance over these k repetitions. Okay, and this k is the k in here is just an arbitrary number. It depends on your model, but if you are working with a machine learning method, sometimes it takes days if your k is really high in here. Okay, and so what is happening in repeated holdout, that this is one set of holdout, and for k steps you are just splitting your training and test several times in here. And for one of them, let's see in here, we have our training data. Again, we are training our algorithm by using this guy. And when we just want to look for the model performance, which is delta I, we are just using test data set. This is an unseen data by the algorithm in here. And after we find all the deltas from each set, each data sets, and from the schema in here, we can find the average value from these deltas in here, okay? And at the end of the day, so we have our performance now. At the end of the day, we have to run the last model with our whole data sets like before and just generate our final product in here. And now I just wanted to add a repeated holdout graphics from the book, the ISLR book. So in the left plot in here, this is just generated by 50 stratified training test split with 75 samples in the test and training set each, okay? And you see that we have 50-50 train test split in here. And 3 nearest neighbors model was fit to the training set, and it is evaluated on the test set in each repetition in here, okay? You just run your model with your trained data sets in here, and I mean in one of the repeats, okay? And the 3 nearest neighbors, and then you just test that model in that repetition, and you just repeat it, this guy, for 75 times in there, okay? I'm in the 50, I guess. Yeah, we have 50, sorry, I said 75 in here. And so the average accuracy, maybe you see that this is our average accuracy measure of these 50-50 splits, which is 95%, okay? So we just repeat the same procedure on the right plot in here. And now the test sets consist of only 55 samples. Okay, we have 90-10 train test split in here. And average accuracy over these 50 split was 96% this time. And now this figure just demonstrates 2 of the points that were previously discussed. Maybe we discussed it before. First, we see that the variance of our estimate increase as the size of the test set decrease in here, okay? And we have higher variance in here when our test split is decreased in that sense. And second, we see a small increase in the pessimistic bias when we decrease the size of the training set. Okay, we withhold more training data in 50-50 in here, which may be the reason why the average performance over the 50 splits is slightly lower compared to that one. Okay, when you just check out for this part. Bias is just the ones that you can see how these guys are fluctuation in this part, okay? And you have less fluctuations in here because you have 50-50 train test split, but in that part you have more fluctuations in here, okay? And for n-fold cross-validation, let's think about it. N is number of the observations in here. You have your first split, and so these are your xi and yi pairs in here from 1 to n. N is the number of observation. And even we see that as xi, please keep in mind that these x's can be more than 1 variables in here, okay? You may have like the predictors may be more than 1 variables. And now in here, what is happening in n-fold that we just have this single row, okay? We just get that single row as test data set, which is just one pair. Let's say it is x1 and y1. And the rest of them is going to be your training sets, okay? And please keep in mind that when we are talking about n-fold, that means we are just working with single row as our test data, And also you hear this method as leave one out of cross-validation. Leave one out of cross-validation, which is LOOSV in here, okay? So it involves that splitting the set of observation into two parts again. So instead of creating two subsets of comparable size like before, we just have a single observation for test set, or you can also hear that one as validation sets in the book in there, okay? And as a second step, now you just moving to the second part, okay? And this is, let's say this is x1 and y1, and this is x2 and y2, and you just repeat all the steps for each row. So when you have your number of observation as n, so your steps is going to be n again. So at the last step, you are going to xn and yn. Okay, you just choose all of them by one by in this method in here. And now we have leave one out cross-validation. This guy shows the accuracy or performance accuracy in here. You can just compare this one and just one of them is just coming from the one step, and you are just having the average of them, and this part is the error, and by having one minus error you have your performance for this method in here for n-fold cross-validation or leave one out cross-validation in here, okay? And we can also talk about k-fold cross-validation. So what is happening in here that now we group data and give all of them to be in one of the repeats in here, okay? So we have the first one for k-fold, and k is going to be mainly smaller than n, the number of observations. Now you have a group of your data sets, okay? So instead of single row in here, you have some part, and then you move to the second part, and again you move to the last part in here. Now this is not a single row, okay? So what can be the advantage in here is that, maybe you should think about it for a minute by just stopping the video. So the advantage in here is that you have less work because k is going to be much less than the n. Generally it is 5 or 10, and maybe you should keep in mind that it is 10 in default is 10 in Python. Then what does it mean? That you are going to do less work and you are saving some time in there, okay? And especially if you have like a big data or large number of data sets in there, and it's going to be much easier to use k-fold. And now this is, yeah, you have k-fold in here now. And if you look for your k-fold in here again, you have your performance for this guy and this guy and this guy. And again, you are just having the average value for this one, okay? But please keep in mind that you should shuffle your data randomly before running this cross-validation in here. So let's compare different k in here for k-fold cross-validation. So we mainly in k-fold, we mainly randomly divide the set of observation into k groups or folds of approximately equal size in here. And so what we are doing that we treat the first fold as our test set, and the method is fit on the remaining k minus folds in here. And the mean squared error is then computed on the observations in the held out fold in here, okay? So let's see as on the left side of the plot, the left one. So k is equal to 2 in this plot, and I just got this plot from the ISLR book. They just run the auto data, and they just use the auto data and use different types of k-folds in here with these data sets. And so for each of them in here, maybe you see that we have different lines. That means we have different data sets in here. That means we have different random split of the observations in that falls in here. Okay, and for each of these splits, and we just find the mean squared error in here. For example, for k equals 2, you see that for different degree of polynomial in here, for each splits, the mean squared error is really changing in this part. Okay, maybe you notice that the variance is really high, but when you just check for the k equals 10 in here, for different degree of polynomial, this is tenfold cross-validation, maybe you notice that now your mean squared error is shrinked and we have less fluctuations in here now. And you may easily notice that the leave one out of cross-validation is a special case of k-fold cross-validation in which k is set to equal n in here. Okay, this is leave one out cross-validation. And in here, you see that we have one mean squared error for each degree of polynomial in here. Okay, and data is, in these examples, data is shuffled several times, and for each polynomial degree of the model, MSE is found. When you just check out for the graph one more time, you will see that we have the highest variance when we have k as the smallest value in here. When we just go over the k-fold cross-validation in here is that, so this is what is happening. We have our test and training data sets. And now we, for the second step, we have another test set. These are not overlapping. And for the kth one, we have our last test and training sets in here. For each of these data sets or for each of these shuffles, they are all shuffles in here. For this training data, we are just running or training our data sets. And when we just want to find the performance of the model or the accuracy of the model, we are just using the test data set as before. And this is what we have for final accuracy and the average value of each of the average value of them. And our final product is just found by using the whole data sets in here. Okay, we just go over the k-fold cross-validation schema one more time in here. So it may be a better idea to see two different cross-validation methods on one slide. And the left one, the schema is the repeated holdout, and the right one is for k-fold in here. And you see that we are just splitting our data sets into training and test in both methods in here. And please keep in mind that at the beginning of this cross-validation, we are just shuffling the data sets once. And it is same for the k-fold cross-validation. You just shuffle your data set once at the beginning of your method in here. And maybe you notice that in repeated holdout in this part, one single data point can be chosen several times, but it is not possible in k-fold. And this is the most obvious differences between that repeated holdout and k-fold cross-validations in here. So I wanted to add one more example, which is more obvious, I guess, in here. We have one sample, and we have, the first one is our holdout method. And you see that we just split the data into two. And the first one is the training data, and the second one is test data. They call it as evaluation data. And when you just check out for two-fold cross-validation, you see that one. There is no overlapping for these data sets. And also for repeated holdout, you see that we are just repeating these methods several times. And when we check out for this one, we may have some overlaps in here. So here is another method. For today, it is more statistics oriented actually. Bootstrap is highly powerful statistical tool that can be used to quantify the uncertainty related to given estimator or statistical learning method in here that we were really looking for in our examples for today. And so let us assume that we would like to compute a confidence interval around a performance estimate to judge its certainty or uncertainty. And now you can give more details or more information about the performance of your model by using this method in here. And so how can we achieve this if our sample has been drawn from an unknown distribution? What I mean is that if you are really familiar with the statistical methods, you may notice that we have some distribution assumptions. And if we know the distribution of that sample, we can easily find some statistical inference or statistical information from for our data sets. But if we are not familiar with this distribution, or if we do not know that distribution for our sample, we may not be able to use that classical methods in here. But what can we do that? We may use the sample mean as a point estimator of the population mean. But how would we compute the variance or confidence intervals around the mean if its distribution is unknown? It may not be possible for you to find a confidence interval if you do not know that distribution in here. So what can we do that? What can be the solution in here is that we may collect multiple independent samples in here, then it is going to give us some idea about the variance or confidence intervals maybe. But in real life, is it really possible to collect several samples or several independent samples in there? It may not be possible for many cases. So what does Bootstrap do that? That method is just resampling technique for estimating a sampling distribution, and in particular we are interested in estimating the uncertainty of a performance estimate, and which is the prediction accuracy or error in this context in here. And the Bootstrap will help us to give more information about the performance of our model, and by not using any distribution assumption in here. Let's see how it is working. Here is the sample in here. Let's see. This guy is our sample with number of n, and your sample size is n in here. So what is happening in Bootstrap is that you are just resampling several times with replacement. And that is why that these trees are circled. You can see one observation several times. And this can be my first sample and second one and the last one in here. And please keep in mind that we choose them with replacement, and training data size is generally n in here. And because this sample size is also n, this one is also n, and this one is also n. The sample sizes are the same with the first one, okay? And so this is going to be our training data sets. The data points which are out of bag is the test data sets. When you choose with replacement, you will see that you choose some variables twice or third or several times, and some guys will not be seen in your other samples in here, and then they are going to be your test data sets. Let's assume that this is the all guys I'm just getting from my sample, and you will see that I don't have 1 and 2 in here. Let's assume that there's no 1 and 2 around here, and I can use these two guys as my test data sets. And it is a useful way to gather statistical information from here, and it is useful especially for smaller data sets. Yes, especially if you have a smaller data set, you can just resampling your data set with several times with replacement and just use that samples in your analysis in here. And also it has a fancy name in here. Okay, I want you to go to ISLR book in this example and check out for details, and I will give that reference at the end of the video. And maybe it's a better idea just to check out for some details in here. But if you are a statistics student, maybe you are really familiar with this concept, you may just skip that part for you guys, okay? So let's go back some steps, and please remember that we were just seeing that resubstitution validation method, and we thought that it may not be a good approach for estimating the generalization of our performance of the model in here. And since we want to know how well our model generalized to new data sets. So because of that, we just move to the holdout method to split the data sets into two parts, a training and an independent test data sets. So now we will try to see that if it is possible to use that holdout method for hyperparameter tuning in here. Do you remember that before that we thought we just fixed the hyperparameters and then just use some models in there? But now we will also try the hyperparameter optimization in here, or hyperparameter tuning. So you can think the process of hyperparameter tuning in here and model selection as a meta optimization task, okay? So it's like one step further. After the tuning stage, selecting a model based on the test set performance seems to be a reasonable approach in here, I guess. And while the learning algorithm optimizes an objective function and on the training sets in here, hyperparameter optimization is another task on top of it in here, okay? It's around here. We have one hyperparameter for this one, another hyperparameter for another one, okay? We are kind of trying to optimize that, and we typically want to optimize a performance matrix in here, such as like a classification accuracy or the area under a rock curve in here, okay? And now I want you to just stop the video and think about the answer of that question. How can we use it in linear regression? And if you think about it enough, maybe you can see that it does not make sense for something like linear regression, because we do not have any hyperparameter in here. So please keep in mind that this is a method that can be generalized for several machine learnings, but maybe not for linear regression in here, because you do not have hyperparameters in that one. And so one solution for that approach is the three-way holdout methods in here. And you know how well our model generalized to new data sets, and by using these holdout methods, and we can just split the data into two parts, a training and an independent test data sets. But the question is, can we use the holdout method for hyperparameter tuning? And we already know that the answer is yes, with a slight modification to the initial approach by splitting data sets now into three parts: a training, a validation, which is new for us, and a test data sets. And why three in here? Because after the tuning stage, selecting a model based on the test set performance seems to be a reasonable approach in here, but reusing the test set multiple times would introduce a bias and the final performance estimate, and the result is going to be optimistic estimate of the generalization performance in here, okay? Because of that, we want to just use three different data sets now in here, and of course it's just giving some disadvantage, then you have less data set for each step. But for many machine learning methods, we have really big data sets in there. Here are our three goals that from that paper. We want to estimate the generalization accuracy, the predictive performance of a model on that unseen data, okay? And we want to increase the predictive performance by tweaking the learning algorithm and selecting the best performing model from a given hypothesis space. And we want to identify the machine learning algorithm that is best suited for the problem at hand, or statistical learning algorithm in here. And thus we want to compare different algorithms, selecting the best performing one as well as the best performing model from the algorithm's hypothesis space in here. Okay. So let's see what will happen now. We will try to find an unbiased estimate of that generalization performance in here. First step is just splitting the data in training, validation, and test. So now we have 3 different data sets. As a first step, this is an outer loop. And for each of j from 1 to m, this means we have that set of hyperparameters j in here, okay? For each of these hyperparameters, we are just training our data in here for each set, okay? That means we are just running that one m times. And we use that validation set, which is unseen in here, to see the performance of each model and just find the performance in here, okay? And this is how it happens. And we just choose the j, which is the hyperparameter now, which gives the maximum accuracy in here, okay? And now in this step, we are able to just find our hyperparameters. And for another step now, we can just merge these 2 data sets. And we will just use the set of hyperparameters we choose previously. And now we are trying to kind of generalize our performance. And by using this test data set, which is not seen before, we are just running the model and with test data sets, and we are just finding this performance for this one. And now, the last product again, as before, we have whole data sets and our last model and our product in here, okay? If you want to use the k-fold cross-validation, we have training and test, maybe you remember. And now what is happening is that for I equals 1 to k-fold, we are just using that training and validation, okay? Training and validation in here. So let's see what will happen. And for these training data sets, for each fold, we are just using set of hyperparameters j, and then we use that validation data for model j. And for this j, we are just using for each step in here, we are just using that accuracy measurement, okay? And we repeat that one for k times. And now we are able to find the maximum of this accuracy, and we will use the corresponding j in here as our hyperparameter. You see that this is an outer loop actually. And now we have our training, which is the merge of our training and validation before. And we are just running or training our model with this j, with this guy in here. And now we are able to just generalize our model, or the performance of our model by using test data sets. And again, here is our the last product that we have to run that guy and with our whole data sets one more time, okay? Here are the references I used to prepare this video.